It's great to see everybody. Wow, I feel like this is like my first time back on campus, even though I've been here a little bit, but this is the first time I've been in an audience. So I'm really excited to have Xiaoji here, Xiaoji Chen. She was a graduate of our program, and I'm really looking forward to the things that she's going to talk about and share with us today. I want to welcome all of you here, particularly both those in person and also those online, watching through our digital platform. And this is one of the first talks this year for the Design and Computation group. So I'd want to first acknowledge the indigenous peoples as traditional stewards of the land and the enduring relationship that exists between them and their traditional territories. The land in which we sit is the traditional unceded territory of the Wampanoag Nation. We acknowledge the painful history of genocide and forced occupation of their territory, and we honor and respect the many diverse indigenous people connected with this land and on which we gather from time to time immemorial. We're excited in particular because Xiaoji graduated from our computation group almost a decade ago. She's been doing a lot of great things. But to start, she was a graduate of Tsinghua University before coming to MIT. She graduated from MIT in about 2011. Her thesis, her SMARCS thesis, was entitled Seeing Differently, Cartography for Subject Maps Based on Dynamic Urban Data. Today, Xiaoji plays two major roles in the work that she is doing out in Seattle. She is chair of the Technical Steering Committee for the Urban Computing Foundation. She is also a senior software engineer at Microsoft, and before that, she worked at Uber, Xbox One, and Visual Studio. While at MIT, she also worked with the Sensible Cities Lab, publishing projects and writing papers with Colorado. And today, her talk, Our Own Legacy, From Passion Projects to Sustainable Solutions with the open source community, is where Xiaoji will share with us her amazing journey, one that she shares with creative coders, technical artists, civil hackers, and entrepreneurs. With this, she's part of a community of very creative coders who I myself have learned to understand how difficult that is, bringing people like that together. But they all share the development of a widely used open source data visualization framework. For those of you who are watching online, feel free to post questions wherever you are, throughout one of our live webcast portals or through Facebook. If you're here in person in the audience, please use the microphone, the one in the back, at the back, and we will answer questions online and in person right after the talk. So I just also want to say that I really appreciate and remember Xiaoji as a student in my class. She made a beautiful chair. I often show it. I haven't forgotten it. And it serves as a really great guide for a really beautiful expression of experience and a really great work of art and craftsmanship. So I really appreciate it. Xiaoji Chen.
Thank you. That was very kind. Hi, my name is Xiaoji. For the first part of my talk today, I'd like to walk you through the stuff that fascinates me and how the journey led me to places that I didn't know I'd go to. It all started with my obsession with maps. As a student in architecture and urban design, it was only natural, right? Here we have 3 maps of the world from the 11th, 16th, and 21st century. The advancement of nautical navigation, mathematics, camera and sensing, and aerospace technologies really give people increasingly more insights into what the world really looks like around us. But can we, as a result, say that the world maps we know as of today are true? Growing up in China, I learned about the world using maps that split down the middle of the Atlantic instead of the Pacific. The most commonly seen projection, the Mercator projection, greatly exaggerates the size of Europe, overlaid with the Peters projection and equal area projection. It's apparent how much we tend to underestimate the size of Africa and South America. In fact, the history of maps being used for propaganda is probably as long as the history of map itself. The 20th century especially saw state-backed press and publishers perfected their craft to manipulate the reader's perception with intentionally chosen iconography, colors, and shapes. There are technically infinite number of ways to unwrap a sphere onto a 2D plane. Not one projection can preserve all the geometric properties of the 3D world. When we choose a projection, when we draw a map, we inevitably introduce distortion and bias to the information that we're trying to present. Arguably, there is a subjective element in every map, either consciously or unconsciously. To me, the subjectivity in maps is not a bug, it's a feature. It's the part that is inaccurate that makes them so fascinating. This is called a mappamundi, which is a medieval European map of the world. The Earth is divided into 3 continents, and Asia is the upper semicircle, and Africa and Europe are each occupy a lower quadrant. The buildings and characters on it do not just represent what's there. They depict wars, the birth of Christ, mythical creatures that co-inhabited the continents alongside its people. This map has a narrative. It is rich with details about what the people of the land believed and how they connected. This was how I first got started with data visualization. I wanted to make maps that challenge people's preconceived notions of what the world is like. I wanted to tell visual stories of our times. This was a project I did with the Sensible City Lab back in 2010. AT&T gave us access to hundreds of millions of anonymized phone calls. And looking at that data, you see from where to where people are making these calls. And just by charting who's calling who across the United States, we're able to analyze how cities operate on an ever-before-seen personal level. We hypothesized that if people call each other more often, that means organically they belong to the same community. So if we cluster mobile users this way by how much they communicate with each other, interesting patterns emerge. People do not socialize with each other by political boundaries. If you look at this map, New York is split into 2 states, upper and lower state, so is California. West Virginia and West Pennsylvania are one, and New England is one big cozy family. We did the same analysis with British Telecom. The country turned out to be communities organically formed around big cities, again, not bound by administrative boundaries or structures. One interesting observation is that when the team was fine-tuning the network partitioning algorithm, we find that even with very similar modularity outcomes, mathematically similar partitioning manipulations, the map could look quite differently. And it's possible they eventually got read into a little too much politically. If you look at B and C, they yield almost the same modularity, but they look very different. In a way, it was proof how prone we are to subtle visual cues when we read maps. Around the same time, I grew very interested in how people navigate and construct mental models of urban spaces. This cover by Saul Steinberg illustrates how personal experience is reflected in the way we think about the physical world. The places where more things are happening relevant to us, to the observer, is perceived to be larger. It was so wrong and so wonderfully true at the same time. I wanted to see if I could draw it quantitatively. Here's the idea. Say I'm going to Disneyland. I walk from home to the transit tunnel, take a train to the airport, fly to LA, rent a car, drive to Disneyland. I think of the segments of this trip by the length of time. If I draw them on a map, they likely look like this, way larger space in the middle than I care to know. Which map is closer to my reality? By injecting transit data into a regular map, I can transform it from being proportional to physical distance to being proportional to travel time or to the mental distance between places. The result is called an isochronic map. The map shows what the city feels like to me in real life. My approach was to select a few hundred transportation hubs in the city, calculate the travel times between each pair, and then let them drive the distortion in a force-directed model. I implemented this algorithm using processing and SVG maps. This was an early prototype using Paris metro stations as reference point and Google Directions API to calculate the travel times based on different modalities. On the left is an ordinary map of Paris. On the right is an isochronic map of a car driver starting from the Notre Dame. You can see that the center expands because of traffic jam, and the edge of the city contracts due to the freeway, but they all connect smoothly, and it preserves all the topological features of the map. When we use different travel modalities to draw the same map, you can see that Paris looks quite different for 3 types of transportation. This is a highly personalized approach to cartography. What the city looks like depends on where you start from, your means of transportation, the time of day or week, and even what special events is going on. You can imagine having a mobile app on the phone that draws this map. It's only true to the context of the user. Same 3 maps, but using carbon footprint instead of travel times to map the distance. I played with different mapping and data sources there. This was under the same umbrella in 2011. We worked with the Singapore government to look into very detailed GPS traces of the city's taxi trips. This is an early plot I made for my partner data scientist and I to study the raw data. Each entry of GPS reading is a dot on the map. The map hardly tells me anything other than the population distribution. But when you plug it into the isochronic map model, it starts showing some very interesting patterns. The final visualization I submitted was shown at the Singapore Art Museum with this complete UI. It was shown on a large touch screen where users can tap their location of interest and see the form of the city change over time. You can almost see the city breathing through the rush hours and clearly identify the clogging points of the traffic. The exhibition lasted about a month and was one of the more popular items. I originally designed it to work with live streaming data, and we set up the application and the algorithm behind it that way. But eventually, that was rejected by the city due to public security concerns. At the time, specialized tools for making custom and interactive data visualization were just starting to emerge. Processing was still the cool kid in town. I don't know if anyone still uses it. That was based on Java. A Stanford PhD, Mike Bostock, caught people's attention with a JavaScript library called ProtoViz, and later turned into D3.js. Now that's the golden standard for data viz on the web. Oh no, the whole thing was still tedious and non-repeatable process. For every project, there was a lot of ad hoc scripts and manual massaging of data to get it off whatever data source there is and clean it up and get rid of all the bad readings and try to map it to geometries. And in the end, at the time I used Illustrator, so I could do this adjustment with feedback. In short, it was mostly a craft of black magic. If I go back and see my scripts from 2 months ago, it probably, I don't know what they do. And, but I felt pretty good. I felt I got the hang of it, and I graduated in 2011, and I was ready to get a job as a data viz professional. To my dismay, there didn't seem to be many opportunities. I wrote pretty much to everyone I heard of that worked in the data visualization field. Many of them ran design agencies. They were hired by museums to set up a show or a company to make their data report look prettier. And because data viz in this context always feel like an afterthought, is we have something and we have to make it look better. The real world projects were far less interesting than their free explorations. I interned at Microsoft as a visualization designer. I prototyped an extension for Excel that made highly custom plots. And when I ran user studies with Microsoft employees, I realized that people think of very different things when I say the word data visualization. For some that I talked to, data visualization was to make an animated pie chart for people who find numbers hard to read. It felt almost like an insult to me and to my users' intelligence. So I went on to become an interaction designer for a consumer product that did make some money. During my time there, I constantly struggled with how disconnected the design process was. We were designing user experience for gamepads, for air gesture, and for voice, but designs were made in Photoshop and Illustrator. I have sit in a meeting in front of a static image where people argue if there's enough feedback for the user input. It took months of debates for any design decision to make into the product, and then someone pointed out that it doesn't really work. I was at the team, I was a fierce advocate for interactive prototypes. I told every designer I worked with that they should try learn to code. I even spent a lot of time creating a tool for them to turn an Illustrator drawing into an interactive prototype. To me, it was not just the ability to test things out. Tools are like languages. They frame how you approach design. If the tool doesn't allow you to make a curve, you don't design a curve. If the tool doesn't ask you to set kerning between your characters, you don't think it's important. After a while, I started to ask the question, why are designers stuck with Asian tooling when we claim to be creating the future? Why are we content to let the arbitrary commercial software products define how we think? To carry out your design ideas, you need some means to execute your vision. At the start, your idea is heavily influenced by inspirations that include prior work and your own goals or ideology of what design should be. The closer to delivery, the more real your work gets, now heavily shaped by resource constraints and technical limitations. In a perfect world, our tools will grant us full freedom to explore design possibilities. And arguably, there is a way to do anything if we have unlimited time to pursue it. But in reality, we often find ourselves confined by the tried and true workflow, and those are usually defined by for-profit software vendors. If they deem some feature not profitable, then you don't get it. Academia, on the other side, see much higher degrees of freedom. However, this work usually prioritizes publication instead of making the techniques readily available and reusable. When a student graduates, they can't wait to open the next chapter of their lives. I know that was true for me. Their work, no matter how brilliant, got buried in a list of citations. It happens because making a tool available is hard. Your proposed approach will be challenged by real-world use cases and users, not just the handcrafted scenario that works so beautifully in your own paper. A new technique makes its way from a paper to a consumer product is painfully long. And much of the work from academia end up contributing much to the inspiration bucket, not the techniques. Another factor that I think went into it is partially how, at least when I was in the design world, how the mentality or culture worked. I did not have anyone to ask how to make visualizations when I started, and whoever sees my work and wants to do the same is supposed to figure it out on their own. usually when we share design outcomes, we like to talk about the philosophy behind it. We like to showcase all the beautiful visuals that's associated with it, but we don't talk enough about how we did it. And even some designers use this exclusive know-how as a competitive advantage so they can make something that other people cannot. So instead of building on each other's work, we are instead protective, paranoid, and exhausted. Fast forward to 2014, I visited my friend Sean, also a design competition alumna, who is now working at a newly formed data visualization team at Uber. I was so jealous when I saw the kind of data she got to work with. Uber sits on troves of unique data documenting when and how people travel, down to each second and each square meter. And simply plotting the GPS traces out, you get this beautifully detailed fabric of cities purely formed from the movement of its people. Have San Francisco, Sydney, Rio de Janeiro, Jakarta, London, Paris, Mexico City. And at the beginning, the database team was asked to just make PR pieces. The team wants to have some flashy new video to show off how fast Uber is growing. And it did a lot of that. But the head of the team, Nico, had a very different vision of what data visualization as a profession could achieve. A great example was how the team told a story around the Uber pool data. They took the record of all passengers who shared a ride with others in San Francisco and ran a simulation of how many cars would be on the road had everyone taken their separate rides. Seeing them side by side, you really see the reduction of traffic by simply enabling a feature in a mobile app. This effort coincided with the period of time when the ride-sharing business was expanding exponentially globally, and transportation authorities in cities started to scrutinize what impact it had on traffic congestion and road safety. Uber ran a few pilot initiatives to share its data with cities, but the outcome was poor. One of such programs was with the city of Boston. Uber shared anonymized, aggregated block-to-block trip data with Boston. We're still talking about terabytes of data per day. The city did not quite know what to do with the raw data. They did not know what conclusion they can draw from so much information, and they decided that it was because it was not detailed enough. It asked for precise GPS coordinates for each individual pickup and drop-off. Now, Uber's legal team became nervous because that could be used to identify an individual and violating its user privacy. And Uber's policy team was also nervous because the city could draw any conclusion from the data, most likely they don't agree with, and use them as evidence against the company. So the partnership fell apart. The first project I was involved in when I joined was to tackle this problem. I know from my own background how valuable Uber's data was to understanding transportation patterns in cities. I believe that independent research and data-driven policymaking would benefit everyone, and a company this size could do better as a responsible participant in our fast-evolving urban lives. The idea was to build an open data platform that addresses all the above concerns. Instead of sharing a raw database dump and leave the reader to make sense of it, we would provide tools to explore that information and use storytelling to demonstrate how that data could be useful. The tool called Uber Movement was launched in 2017. The travel times data set is currently available for most cities that Uber operates in. It allows anyone to look up the average time it takes to travel from point A to point B in the city at a very specific time. Travel times was a metric that many transportation departments already collect by deploying cameras and field operators or hiring a third-party contractor. It took a lot of manual counting and was expensive and could be weeks or even months behind. Using Uber's data, they could see it in near real time. The tool allowed the user to craft very complex queries by any combination of days, weekdays, and hour of day, continuous or non-continuous, and you can then compare the query with another query with equally complex conditions. There are also 4 different data tables you can download for any view aggregated by different methods. We got all of these by working with multiple cities and make sure the tool is productive for them in their professional operation. On the other hand, the platform was open to everyone, anyone, especially what we call civil hackers, were allowed to go there and get that data, and the freedom can be truly overwhelming. We countered this with curated stories that showcase the power of the data set. This story was inspecting how the annual Boston Marathon affected downtown traffic. This map is generated by comparing travel times on Saturday, April 16th of 2016, the day of the marathon, against the average travel times of the previous 6 Saturdays. Red is used to show travel times longer than usual and green shorter. From the more detailed charts, you can see the travel time spiked starting 7 a.m. and the main event kicked off at 8 and completely died off after 5. In my observation, introducing a visualization with a clear narrative has always been a powerful way to engage the audience. These narratives may not cover the full virtue of the data set, sometimes may only showing one of many possible interpretations, but what they do is that they inspire the audience to come up with their own stories or theories and explore on to challenge them. Cities already use this data set to measure the impact of a major road closure or compare the before-after traffic after they implement some traffic laws. They can now get instant feedback on their decisions like never before. On the top left was one study we run looking at the food desert problem in Cincinnati, or looking at how long people take from where they live to drive to the closest grocery store. And there are little trapped areas in downtown where it's almost always low-income communities where it's very difficult to get healthy food within a reasonable travel time. On the bottom left, we have the March flood affecting travel times in Nairobi. And on the right, we see how a small outage in one segment of the metro service in Washington, D.C. propagated in a domino effect and affected how car traffic worked in the entire city. The platform also contained other data sets, for example, per road segment, travel speed, and multi-modality data showing how people are traveling, either by bike or by car. The project was a big technical challenge as petabytes of raw trip information is constantly being processed to churn out these information we want to show. And we need to make sure that all data are properly anonymized and correctly presented. The whole thing runs in a browser. And no matter how big the data set is, it's very important to be fast and responsive when the user interacts with it. It was during projects like this, the DataViz team realized that existing JavaScript libraries were not meeting the challenges of modern visualization on the web. The most common approach championed by D3.js was drawing in SVG. It works great when you have up to a few hundred visual elements. But when we work with trips and locations and street segments at Uber, it's common to be rendering millions of points and lines. We looked into a technology called Webgl, which allows the browser to tackle the power of GPU directly from the browser. I stole this diagram, and it shows how CPU and GPU works differently. CPU is a big pipe. It has very powerful processors and can do a lot of work very quickly, but it's a single pipe. For GPU, each core is less powerful, but in return, you get parallel processing. It can do a lot of repetitive work at the same time. If you think of visualization as a mathematical transformation of data from bit representation to pixel representation, then dealing with a large amount of data points is essentially repeating this transformation over and over again, and GPU is precisely designed for that. The DataViz team created a library called DACGL. DAC refers to the layered approach to visualization. Each layer represents one such mathematical transformation written as shader modules that directly instruct the GPU what to do. Here you see DACGL rendering almost 1 million geolocations as a scatter plot at 60 frames per second. All that the CPU does when you interact with it is to calculate the new map center and zoom level and tell the GPU to recalculate where each point should be and what color they should be. The GPU is performing the web Mercator projection on the fly at the necessary precision at a very high frame rate. GPU also allows us to do data filtering on the fly. Here we are restyling 320,000 arcs based on mouth position. So again, CPU only sends the pointer position to the GPU, and the GPU is figuring out what to show and what to hide. This demo shows DACGL aggregating 4.5 million data points on the GPU. Every time the user zooms or pans the map, it recounts the number of points in each of the tens of thousands of grid cells on the screen. As the Webgl 2 standard got implemented in modern browsers, we also embraced it and utilized the capability to offer more powerful GPU processing. This demo of highway safety in the United States colors every road segment by fatalities per mile. The GPU smoothly interpolates between two sets of over 400,000 vertex colors as the year changes. In April 2016, we open sourced DACGL. We put the entire code base on GitHub and under the MIT license, which is a very permissive license. Anyone can basically do anything about it. We promoted it through an engineering blog on Uber's official channel. As of today, DACGL is one of the most comprehensive and widely adopted visualization libraries using Webgl. We're working on a growing catalog of layers addressing diverse visualization use cases. Here are just a few examples of what you can make with just a few lines of code. Uber's attitude towards open source was typical for startups and very different from the old world corporates. Its entire tech stack is built on open source tools, and in return, it does not mind giving its own work back to the community. The work we did there were open source by default. When people outside of your organization start using your libraries, they identify issues in edge cases that you haven't encountered yourself yet. And they challenge you to think about more generic purpose beyond the requirements of your immediate project. And they constantly push you to solve more complex real-world problems. That dynamic helped us make the libraries more robust and more powerful. Soon, the validity of DACGL got put under its biggest test yet. The DataViz team proposed to make the tools for developing autonomous vehicles at Uber to move them onto the web. To understand the challenge, let me explain the complexity of the data itself. The self-driving cars and trucks are equipped with a rich suite of cameras and sensors. They see way more things on the road than human drivers do, and they are capable of making decisions many times a second. For human engineers to understand why self-driving cars act a certain way and further iterate on the software, they have to make sense of the context where these decisions were made. What makes this product so challenging compared to the previous DataViz projects started with how much data I have to show on the screen. Let's just break this particular view down. At the beginning, you have the city context. This from a macro level. You have the base map, the road network that connects the origin to the destination, the buildings and addresses and ground imageries. These are essential for humans to make sense of the environment. And on top of that, you have the AV map. We have the autonomous vehicle maps. The maps contain every meticulous detail. For example, the lane boundaries. Is it a bus lane, a turn-only lane? What's the speed limit, street signs? How many traffic lights control this lane and where they're located? This information represents what a car knows about the road condition and restrictions prior to a trip. And last but not the least, you have vehicle log. That is everything that happens in operation during the car's trip. In this video, you see the autonomous vehicle itself driving through an intersection and with the front-facing camera feed. The bounding box of other vehicles and pedestrians all moving and updating every frame. They're what the car sees on the street. You may have noticed that we draw the features of the road in more or less unrealistic fashion, like the signs and the traffic lights. But everything else is a very abstract visual language. We had to develop a set of abstract visual language for the vehicle log because the complexity of the log is 2 dimensions more than map data. It does not just describe space, but also describe probability and time. There are 3 critical stages of algorithms that run during a AV trip based on sensor data. We have perception, which is what the car measures. For example, what objects are around us. Are they cars or pedestrians, and how fast are they moving? We use color coding to show the classification of the object on the road. At times, each object in the scene may have more than 1 bounding box if engineers want to see the alternative shapes that were considered by the algorithm. For that, we can use slight variations of these colors for each classification. Then we have prediction, which is what the car forecasts. Is that car going to turn in front of us? Where will it be 10 seconds from now? Note that predictions naturally describe possibilities of the future, and they may change at any moment given new information. And now it becomes a very interesting visual design challenge because you are illustrating something that are slices of time from the future, but are only relevant to the present. For prediction, we draw a path from each object, that is the projected trajectory, and dots along the path represent where the object is expected to be every 0.1 seconds. By looking at the density of the dots, you can tell how fast each object is moving and whether it's accelerating or decelerating. Again, alternative trajectories may be considered by the algorithm, so each object may have more than 1 predicted trajectories. And on top of that, we have motion planning, which is what the car decides to do. Are we changing lanes? Are we stopping at the light? These are all reasonings that go into the car pressing the pedal or turning the wheel. Similar to prediction, we draw a wide green path from the car that is planned trajectory, and every dot on that path shows the position where the car plans to be in the future. For engineers to see if planned trajectory is going to get too close to an object in the future, something called a look-ahead capsule is used, where you have a ghost of the car and each other players on the road coming out, and you can drag a slide that sees where they will be in each given future timestamp. And if we're dealing with simulations, we could even have multiple cars on the road where we show what would have been if presented with a different set of environment inputs or algorithm. So before my involvement, the only generic purpose visualization tool that this group had was an ad hoc desktop software. It loaded maps and logs from files on a disk array in their Pittsburgh office, and you can only use it on a particular build of Linux and a particular build of hardware configuration in the office physically. And because of all sorts of plugins that people have built for it over the years, it took minutes to start up. So the group spun off from CMU, from a robotic lab from CMU, and this was a legacy application that they initially reached in an academia environment. And you know how that is. It worked for its time and served the early development well. But like every organically managed software project, they eventually failed to scale. And we presented attractive arguments for moving this to the web. It will be hardware agnostic. It will work on anyone's laptop everywhere. You can work from home. It will allow us to iterate with fast cycles. We can just deploy a new version, and you hit refresh, and you get the new version. And then it also allows to make better customization because the web naturally offers richer UI options with all the libraries that are available out there. And the main concern many people had, because a lot of them were skeptical, was whether such a tool would be performant enough to work from the browser. They argued that the browser would never support the kind of performance that is required to render millions of data points at high frame rate. Let's look at the complexity that the computations that are involved when we do such renderings. Humans and autonomous vehicles consume geospatial data in different coordinate systems. The base map uses longitude, latitude. The autonomous vehicle map is divided into chunks that we call submaps, about the size of an intersection, and where all road features are measured relative to their own submap center. And then the vehicle log, that is the runtime log, measures everything in relative position and orientation from the pose of the car. Now, every single snapshot of a log contains at least 5 to 6 different coordinate systems, and just to match them together in one 3D scene involves a lot of computation. This video, you really see how the DeckGL point cloud layer, GeoJSON layer, and mesh layer come together in action. The 15-second snippet contains over 100 megs of compressed geospatial data downloaded from multiple service endpoints and rendered with over 80 DeckGL layers. Each layer has its own coordinate system, projection method, and styling logic. All layers share a single camera that represents the user's point of view. The positions and colors are being refreshed every frame during a playback, and DeckGL is optimized to handle that extremely efficiently. Because autonomous vehicles is a fast-evolving technology, every week they start producing some new metrics or techniques, and each team at the group has a unique visualization and data generation need. The DataViz team we had was a tiny team, but we aim to support hundreds of engineers, custom workflow, and adapt quickly to their ever-changing use cases. And to do this, we created a protocol for the data service to stream generic 3D data to the front end. Streaming allows us to break the memory limit of the browser and also allow the back end to command what is drawn and how they're drawn in the front end without redeploying the front end app. Internally, the visualization platform was packaged as a reusable module, so each engineering team could build different web apps that all share this one core rendering component, but build their own data logic and user experience around it. This is an example app on the platform built to support the triage use case. So operators and engineers need to be able to go back to a particular point of time to see why the car did what it did. If something went wrong, maybe perception, prediction, or planning phase yielded the wrong results, or maybe the car was not properly executing the commands. In this tool, the user is able to drill down into any object in the scene and look at how it behaved and interacted with others. Then they're able to attach comments and create tickets for the responsible team to further investigate the issue. This is a different app on the platform built to support the debugging use case. Autonomy engineers will test new versions of their software in simulations, so they feed in the same environmental sensing data, it's the same input, and see how the car reacts differently. And this tool allows them to compare the results between two versions side by side or overlaid on each other and see what the difference in performance is. We eventually took the core part of the data streaming protocol and the DeckGL-backed rendering engine and open sourced it as the autonomy visualization system. The URL is avs.auto. I think it's still there. To me, this was a project that really demonstrated how data visualization engineers made an impact in the core research and development process. By this time, we were no longer just there to make good-looking images. The design expertise and the user experience that we could deliver made a big difference in the productivity and the decision-making process that was vital to the business. Everywhere else at Uber, you could also see DeckGL powering essential tools for everyday operation. This was a visualization portal that was used by hundreds of data scientists and operators daily to understand trip records. With a few clicks, it pipes in millions of rows from the data warehouse and shows them on a map. And every aspect of the visualization is customizable without writing a line of code. The tool was eventually open sourced and called Capsule. People are making thousands of maps with it now every day, and won gold at the Information is Beautiful Award in 2019. There's a different app where the machine learning team used Webgl to view and compare the performance of their models. More encouraging was that we were seeing more and more adoption outside of Uber. Dozens of businesses, just what I'm aware of, use Webgl in their commercial products. We see web applications that explore transportation, communication, and urban development in the browser with the intensity that would not otherwise be possible. We see data journalists embedding interactive maps in their reports. We also see non-geospatial use cases where Webgl is used to inspect super high-resolution bioimaging or explore the relationship of hundreds of thousands of cells and genomes. We started seeing contributors from outside of Uber making substantial commits to the code base, and seeing third-party libraries that allow people to use Webgl in ways that we had not supported ourselves. There were bindings for Webgl to be used with R, with Tableau, with Vega, Python, and even a desktop version that directly talked to CUDA, which is NVIDIA's GPU computing package. Webgl has seen endorsement and investments from industry-leading companies like Google, Esri, CZM, Cardo, Foursquare. There are almost 90K NPM downloads daily now, last month. I no longer work at Uber, but the landscape of data visualization as a profession is very different from when I joined. Now you speak of the word data visualization. Most people think of this. They think of solving complex problems, think of showing patterns in data that's otherwise intangible, and think of creating tools that empower non-technical people to do the same. There are job listings looking for data visualization designers and data visualization engineer, and some of them even mention experience with Webgl. I would like to think of the work I did made a positive influence in this shift. I'm also much more optimistic about the way we're working. There is a vibrating visualization community made of creative coders, technical artists, and civil hackers who not only share what they made, but how they made it. They're more than happy to make their code available and reusable for everyone. Tutorials and examples are everywhere. As a direct result, newcomers are able to learn the craft easily if they wish, and feel confident and curious and form an explosion of new ideas. I think we can go to great places from here. For the second part, I would like to offer some reflection on my experience maintaining an open source framework. Webgl was open source almost 6 years ago. Before the ownership was transferred from Uber to the Linux Foundation, I was the tech lead of the data visualization open source team. At the peak, there was 5 to 6 full-time engineers to maintain the open source frameworks. For the last 2 years, I chaired the technical steering committee for the project as a volunteer. In other words, I'm no longer paid to do the job. This XKCD comic hilariously portrays the state of the open source dependency stack. Everyone would like to think if something is open source, then there are more eyes and hands on the code and all comes for free. The reality is sweat and goodwill are limited resource, and they can easily move elsewhere because of a change in someone's life or a shift of interest. They simply get bored or get burnt out. Everyone taking it for granted and nobody making a commitment leaves the ecosystem more vulnerable than we care to commit. There are over 1,200 packages with the keyword data visualization on NPM. Anyone is free to start a new library. The difficult thing is to get people to use it. There was a handful of times when the visit to Webgl's website and GitHub repo saw substantial growth in a short period of time. Each time we made notable improvements in the developer experience. Through answering thousands of issues on GitHub, I have talked to users of the library that comes from all technical backgrounds with different familiarity with web development or with cartography. There were sections in our documentation that got written and rewritten a dozen times until people stop asking questions in confusion. We also redid the format of examples many times, so someone new to the library, even they're not familiar with how modern JavaScript development stack works, can get something running in under 5 minutes. We created multiple flavors of distributions, from pure script tags or to NPM packages and to Python packages, so people can use the library with different sophistication of dev setups. Another visible boost is Twitter celebrities of the database community show off their maps made with DeckGL, or every time engineering blogs of Uber and Google post some article showcasing what's possible. When I think of the course of adoption, there was a tipping point after which the user base formed a critical mass, where just by sheer momentum it was moving upwards on its own. I remember the first time someone I didn't know jumped into a GitHub issue and explained it better than I could ever do, and even completed it with a code sample. I remember the first time someone proficient in Webgl posted a very well-articulated problem, signaling that they were using the library in a very serious way. Once users from Europe and China emerged, I started getting notifications around the clock. And then one day I realized that there were less issues on the weekend than weekdays, meaning people are using it at work instead of messing around in their spare time. Those are good feelings. It's surprising how forgiving users can be, even if your answer is, no, we can't do that right now. When I write a long response detailing why I choose to design the API one way or another, why the limitation is hard to address, and suggest a few possible breaking changes in the future, their response is more often than not, okay, I think I can work with that right now. To these users, they care more about how much engaging conversations they can have with the maintainers, and they care about where the library will go instead of where it is right now. As previously mentioned, in early 2020, we transferred DeckGL to the Linux Foundation. At the time, a consensus among the contributors to the project was that the ambitions of DeckGL had outgrown Uber's appetite. It was no longer only serving Uber's own use cases and was consuming engineering resources that management is starting to ask you questions. And many external users openly expressed hesitancy to contribute because Uber owned the copyright to the code base. By transitioning to open governance, the existing maintainers simultaneously gain more and less freedom. We're happy that we're now free to give external developers write access to the repo, and we can receive sponsorship from other companies. Meanwhile, all decisions for the project must be made in the open. There's no more changes on a whim now. If I'm going to propose a breaking API change or a substantial new feature, there is a process to follow. I have to write a document, and I have to wait for the community to give me feedback before I decide to move ahead, because this could potentially impact a lot of people. I ended up writing a lot of documents that describe the collaborative process of everything from getting maintainer status to opening a PR to opening an issue. And some months I spend more time writing automated tools to enforce those rules than actual shader code, because the project has grown so big that I can no longer personally supervise every change. 3 to 4 times a year, we organize open governance meetings where anyone who's interested in the development of the project can jump in and discuss what features we want to implement in the next cycle before we actually do it. I also spend a lot of time writing code reviews and whisper encouraging words to people who do submit a PR. Even I can do it much faster myself, because having a healthy base of contributors is vital to the sustainability of an open source community. And very popular saying at Microsoft is, if I get hit by a bus tomorrow, everything should keep carrying on like nothing happened. Especially now that no one company claimed responsibility to keep it alive. I see that as my priority. And Many younger companies like Facebook, Uber, or Airbnb maintain critical components of the modern web infrastructure. I don't know if that's a good thing or bad thing. Older giants like Microsoft in recent years have also turned their attitude around. On one hand, they have the financial means to hire top-of-the-line developers to work on these libraries. No nonprofit organization can ever dream of that. On the other hand, as what I have witnessed firsthand, when an open source initiative is not essential to the core business, the company can decide to pull the plug in at any time, and that could be just one manager change away and leave everyone stranded. In recent years, a new monetization model has arisen called the open core. It means that startups release the source code of part of their core solution and withhold other parts, the premium features that they could then charge for as a product. If you have the skills and resources, you can, of course, just build on top of the open source part yourself, or you can just pay them to make it easy. One big risk there is we've seen these projects started out with a permissive open source license, attracted a big following, and get adopted in many tech stacks, and then the core maintainers would withdraw that license and switch to a commercial or closed source license, effectively just shutting it off from everyone. Many contributors felt betrayed, and the reason that happens is big corporates are preying on these communities. For example, Elasticsearch started as an open source search engine, and later the core maintainers formed a company called Elastic to offer hosting for a charge. Not long after that, Amazon announced that they are launching a product called Elasticsearch as well, and they use that open source component of it, and instead they offer their own hosting options. Elastic was furious and switched to a closed source license. Everyone was furious. Amazon immediately forked it, so now the community is fragmented. Everyone's running their own version. You lose the point of open source by that time. The same thing happened in our community last year when Mapbox essentially went closed source after Microsoft and Amazon both launched competing data services that took their revenue stream away. And just direct people to use their free open source map renderer. A more pessimistic friend of mine commented that we live in a dark time for open source. From my perspective, I do understand why companies make the kind of decision they do. I think it's my responsibility as the steward of an open source project to find them the incentive to keep contributing, to keep pulling their efforts together instead of doing it separately. And it would be better off for everyone if we could make it work. If you ever decided to try it out yourself, some advice to stay sane as an OSS maintainer: draw the boundaries, never take things personally. If after a rough day you see someone commented, "Why can't this library do X and Y? 5 question marks is useless." Just put on your phone and don't think about it. I think it helps that I've got another job, that I have a full-time day job that I can go to, and I feel fulfilled in, while that supports me well enough to keep working on these open source initiatives. And after all, it's a very rewarding experience, seeing that I'm solving hard problems and helping other people, and the whole community is creating wonderful things using my work. This was my favorite visualization of last year. This is the GitHub contributions of me through 2020 and 2021. In August there, you see a big gap. I was pregnant. I was experiencing severe morning sickness, and nothing much happened there. And in March last year, my first son was born. And I probably worked a little too hard after that. Going back to the isochronic map, now I can use Webgl to do it. The Java version that I originally wrote when I was in school could handle, I think was 300 something nodes. And this one, we're dealing with 200,000 nodes, and this is capture of real-time transformation as the travel time changed. That's everything I have.
That was fantastic. I think there are so many areas and points that you brought up around computation design and just governance around computation and managing it that I can ask tons of questions, but I'm going to try to maintain and ask a few. The first question I really have is more around, actually before I do that, I want to back up for a second. In the 90s here at MIT, Bill Mitchell gave a lot of talks and wrote a lot about a lot of the topics and subjects that you bring up. One in particular is the relationship between, am I doing something? There we go, thank you. The relationship between people like yourself, people who write code, but you're a designer in many ways, and how the environment is affected by people like yourself who can create software and applications that deal with the environment. For example, like you showed a lot of stuff about related to driverless autonomous vehicles, for example. And I wonder what influence you may have on how the environment is designed. Like I always wonder if any of your visualizations can affect urban designers, planners, architects, civil engineers, people who actually design the streets, people who actually design the physical environment. Have you ever run across a relationship or an opportunity to affect those people?
The movement projects that I mentioned, where we build an open data platform, I know as a fact that it's actively influencing policymakers in different cities. They are using that data to see whether an intersection, the traffic lights or laws they deploy, cameras they put in, are making a positive impact on the congestion or road safety. And I think looking back, I feel that was something that I was really proud about, because by finding the right way to share data, I find an incentive for the companies to continue to do so, and I found a way for cities and urban designers to benefit from the data that the company is sitting on. I think another way is the open source libraries that we made, the tools that we made for designers to look at maps and look at data. If you look back 5-6 years before those things existed, it was actually not easy. You need to have a lot of technical knowledge to be able to draw a map like that, or to explore data and see what it could look like if things were done differently. And now it's been made a lot easier, and I'm working a little further away from the urban planning or design community now, so I can't tell you, names of people that are actually doing things differently. But every time I go to conferences and run workshops of Webgl, there are a lot of designers that come up and express their excitement that it provides them with a different lens to look at what they made, and they can possibly understand cities a little differently now that there are different tools. I think that influence may be subtle, but it's there.
Right. Well, can you see new products coming out of it? Like, for example, once we digitize music, then I can't remember some of the horrible new products that came out after people digitized music and tried to make music players and things like that. We moved from the Walkman to, I forget what the first little thing was called, MP3 players. I wonder, are there new devices and products that you can see people designing that could help out with autonomous vehicles?
Autonomous vehicles, yes, there's a whole industry around it. There are not just people that are developing self-driving cars. There are also a ecosystem of companies that are providing tools around them, and I know some of them that are building commercially available products based on Webgl that help the data scientists or companies that do self-driving cars to understand their data better.
Do you see it influencing the way you design roads and buildings?
Eventually, probably, when we have more self-driving cars on the road than real drivers, a lot of things could possibly work differently. And hilarious anecdote is I used to talk with the autonomy engineers at Uber, and every single one of them told me that they're making self-driving cars not to give up driving themselves, but to have all the other stupid drivers on the road to give up driving.
Right. But I push back because I think about the Apple Newton. The Apple Newton was the device that was prior to, I think it came after the, I can't remember which one, but it was one of these programs where it was supposed to read your handwriting. And then they realized that to get a device to do something as complicated as reading your handwriting is hard. It would be a lot easier just to give people buttons, right? So that's part of how Apple designed its interface. I wonder, in your case, would it be possible to change the interface of how self-driving cars work? That maybe you're still driving a little bit, but maybe the driving component is much, much more simplified.
That visualization is actually also used inside the car in some of the pilot cities in Phoenix and Pittsburgh. When they were running it, you could call over self-driving,
Right.
and you're gonna sit in the back seat. And they found that it's very important when you're sitting in the car to see what the car is seeing. Otherwise, it's very scary. If you see what the sensors are seeing, that the car is seeing all the other cars on the road and making the right decisions, somehow that becomes very reassuring. And that was an important part of the rider experience.
Yeah. I would definitely.
I think Bill Metro had a lot of ideas of, if everything's self-driving or ride sharing, maybe we don't need parking spaces at all. Things keep moving, and we can optimize the congestion away, and we can get away with less cars with the same amount of mobility. I think in practice it's more complicated than that. People want cars for different reasons. They want freedom, or the idea of freedom, and some love driving because the experience that it offers them. It's not just for moving from point A to point B. So I can't predict, when this will happen. It could be nothing happens for 5 years, then overnight, it just went over the tipping point, and everyone's having a self-driving car. Right. You never know.
Right. So I just have one last question to ask you, which is, if our students wanted to get involved in data visualization and programming and some of the things that you showed, what is maybe the core skill that they might need, maybe in terms of either programming or applications learning, and also how would you see them using it? Maybe the first one's easier.
Create a GitHub account. Get on there, read the documentation, see what other people are doing, take their code, tweak a few lines, and see what you can make differently from it. We're talking about JavaScript. The deck.jl is also available with other language bindings. I really recommend JavaScript especially for people without a computer science background. It's something that's really forgiving and really easy to get started. I've taken computer science classes, like the introduction to programming classes, and they want to scare you off in the beginning by talking about memories and data structures, but in the end, I think people in the architecture school are like me. I'm very visual. I get rewarded by making something that's tangible, that I can see, that I can play with, and that makes me want to make more.
Thank you. So we have some questions. Sandy, do you want to take over from here?
Yeah, I'll take over questions. Thank you so much. It was amazing to see all your work. As somebody who occasionally tries to make an open source tool, that was extremely impressive to understand how wide-ranging the impact of what you built is. So I'll open it up to questions. If anyone has one to start, you can go up to this microphone here. If not, I have a few of my own, but any big pressing thoughts? Okay, so kind of building off Larry's question a little bit, looking at this open source framework you've built, I'm super curious how you actually started on that project. Like as a designer, how do you approach a project of that magnitude and then kind of manage the overarching design aspect of it as it grows and develops?
I didn't actually start it. Someone else did. It was, I think he was an intern at the time, and he was doing a PhD in data visualization in UC Davis. It started with a simple idea that we need something more performant than SVG. We need something that tackles the power of GPU. I think it started with only maybe 2 or 3 layers. It drew points, it drew lines, not very nicely. There were no line joints, and there were not a lot of things you can control with the points. You can't do stroke, you can't do, fancy sizing options. But that started meeting the requirements of internal products, and it made some of the use cases tolerable. The performance was become usable from something that was completely a disaster. And that's partially why I don't personally want to just full-time make open source software, because when you're removed from the real world use cases, from the production environments, you kind of lose touch of what is important and what people are actually using it for and how they're using it. If I am personally tasked to make a very challenging, complex visualization tool, then that makes me go back and think about all the design decisions I made. Did I do the right thing there? Could I have done something better? And to me, that keeping touch was like, that keeps me grounded. And that was important. And back to your question, how it started solving real world problems. And we just find out more and more real world problems to solve. And eventually it built up to an enormous frameworks that almost address every aspect that you can possibly think of in the visualization world.
Thank you. Here, you can step up to that microphone there.
So inspiring. Just thank you so much for sharing that. You did share that from academic, the work you did was more going into the inspiration bucket, and you talk about why people don't share about their techniques. I can't help but realize that you started as a user experience designer after your architecture school, both of your architecture school, right? And how did that actually, did that contribute anything but to, you mentioned the tool will Well, actually, what the tool allows you to do instead of, how did you address that? I'm sorry, just like, you want to, like, instead of like a graphic representation, you want to build a tool that actually, because I work as an architect, I just kind of think about like how you use Revit. Like we have the tool for architecture. Like we have to build like a 3D model, a BIM model that we share with the contractor. But most of the time, for like whether for us to save time, we just fake the details to convey our ideas instead of like really build it the right way and give it to the contractor. So I'm sorry that just.
So I don't mean to, say anything bad about being an architect, because I think being an architect is amazing, and I ran away because it was too hard. And I can tell you my reasoning why I chose to go into software instead of practicing architecture. It was because you talk about doing things the right way. It's important to me. Like I think of myself an idealist. Like if I make a recommendation, I want to be able to stand by my recommendation. I want to be able to justify my opinion. But after so many years in architecture school, I found that I was still not confident when I say, I think this is the right thing to do, the other thing is wrong, because I don't know. In architecture, it takes so long for you to get that feedback, for your idea to get built, and for you to actually observe how that space to get used. And maybe realizing I could have done it differently, right? Like it takes 5, 8, 10 years for you to get that feedback. Like how long is your career? Before I have done that repeatedly, who am I to say this is the right thing to do, the other thing is wrong? Then if you look at the structure of design firms, that's exactly what happens. People with seniority basically wins the argument, because when you come down to it, it's a problem of opinions. None of you can prove that what you say is right. And then whoever has the seniority, they get to make the call and say, this is what we're going to do. In software, it's a very different landscape. You have an argument with your program manager, for example. He says option A is better. He said option B is better. Okay, let's put both of them in our software and give 50% users option A, 50% option B, and see how they behave when they see these different things. Who is more confused and who is happier with this? You can get that feedback within 2 weeks. You have solid data pointing to, yes, I absolutely said the right thing, and we should go with this option, and they can't argue with you, right? Like, it's eventually it's not even me trying to win arguments. It's me want to improve myself, wants to better myself as a designer, and that feedback loop is so important that I just cannot find it in architecture. I think we live in a very different world now. Like all these projects that we have, like for sensing and using mobile devices to track people's behavior, they help us understand quantitatively how people are using urban spaces better. And that gives us the means to get that feedback more promptly than we used to be able to do. And I am optimistic that there are a lot that we can do to help close that loop and help people to make more fact-driven decisions and stop having the opinion arguments.
Thank you.
All right, I think we have time for maybe one more question. Okay.
Hi, thank you so much for the wonderful lecture. And as a Webgl user, I'm impressed with its creativity and efficiency. And most importantly, it is an open source library, which is very generous. And in terms of its creativity, I wonder, like, it has so many like interesting layers. For example, a layer to represent the transformation from one place to the other. So I feel like for geospatial data, it's quite different from like other data, which can be represented by maybe pie chart or histogram. So how did you or your team come up with so many interesting layers to represent the geospatial idea? Sorry.
It all started with trips. DACGL is still thought of as a geospatial first library, though it no longer is. Because in the beginning, we did so many interesting examples and so many good layers to represent geospatial data, because that was what Uber had, right? Again, we were trying to solve real-world problems at Uber, and at Uber, a very typical data set is when user get pickup in one geolocation at a certain time and get dropped off at a different geolocation at a certain time. And you want to understand how that movement is working, right? Like in the early morning, people are moving from suburban residential areas to the downtown office buildings, and in the evening they are moving the other way. They were moving to a region that has more restaurants and nightlife, and evacuating where they were in the morning. And those were some of the very first things that the data scientists at Uber wanted to understand. And that's how we came up with the arc layer, right? You want to see how people go from point A to point B and how those places are connected. I think they all came from somewhere. And DACGL is also really built with the idea that we are not dictating how the data should be presented as. It gives the user full freedom to customize layers or even write their own layers and explore how that transformation could work. I think, I work in mostly non-geospatial visualization these days, and I don't usually use the arc layer, and instead like heat map and scatter plot are the more important things for me.
All right,
So,
may I ask another question?
Yeah.
Which is related to the open source.
Yeah.
I wonder if there's something great you can like maybe get some great ideas from the comments of GitHub that might be the advantage of open source library. Otherwise, open source kind of gives you risk and also without profit. What kind of power did you get to maintain that open source library?
I kind of touched on that a little bit. When we initially open sourced that, like the reason Uber was tolerating it and many other companies are sponsoring projects like this was because you get people to test your code for free, right? Like people are trying it in different contexts. They are finding bugs that you haven't seen yourself, but probably will encounter someday, and people are challenging it to be better and be more powerful, to cover more use cases. And many times, like I have seen in that self-driving car visualization exploration, things that were first brought up by other people ended up being vital to a new project that I started working on that, that's in a completely different context with a completely different data set. And I realized that it is possible for me to design the APIs in a more generic way and not just address the immediate use cases at hand, but to work in a way that can visualize a more diverse data sets and in a more complicated scenario. And if we were writing a Webgl renderer from scratch, I would not have taken on that project because that was so overwhelming. Yeah, I didn't think that was possible. Yeah.
thank you very much for your very inspiring talk. And the best part to me today that I heard from you was this politics behind the open source community. And I'm one of these people who are very scared of the idea of being in a car driven by a machine.
You're not wrong.
Yes,
After what I have seen, I would not want to read the music.
but I felt a little bit better to hear from you, and somebody like you is actually watching over the code shared by the open source community and making sure that they properly maintained and probably work really well in a real environment. But that's not my question. I'd like to ask you to tell some message to our students who's studying in architecture school now about becoming somebody like you. Somebody like you who actually, in my perspective, was a very unique student when you were here, equipped with a very sort of fluent command of coding, but yet you also had a strong architecture background, and in the end you found this perfect marriage between the technical world and the topic, which is also interesting in thinking about design, especially the urban designs using data-driven method. Today, and then you went on to the world of big corporation who produces many products, competing with large IT companies. And I think back then, you are one of these very few students who were able to get into that world, and also in the end, you made a very big contribution to the society. Today, I see many students inspired by the idea of machine learning and AI. So I guess some students are interested in following your path, maybe not in data visualization, but making some changes in the world of AI, and especially topics related to architectural design or urban designs. I wonder, you have any message for these people who's interested in that kind of path, who's not maybe as interested in becoming an architect at some point, and dare to get into a new path, which is not an ordinary architecture student path.
I don't think I'm in any position to give other people advices. I think. Let me frame this differently. I can't tell you what will work in your own path, but if you need encouragement, I can tell you that I did not feel like I was getting my dream job when I graduated. I kind of made some compromises, and I moved around in places. Everywhere I went, I tried to define my role, myself. There is a certain expectation of what an interaction designer should be. And as I said, that was using Photoshop and Illustrator and make good-looking images. And I went in and I insisted that everything should be interactive. We should build prototypes and test everything out before we tell the product team, this is what we want you to build. And however small an impact, I felt that I changed how people look at the design process around me. And eventually, along the way, I found something that I really enjoy doing, that I feel like is kind of kind of gives me a purpose in life. And I don't mind keep doing it even I'm not paid. And for anyone that wants to deviate from a standard path from your education, I can't tell you what's gonna work for you, but if you want to look for an example, I can say that look at me, you can find it eventually. Stay committed to what really inspires you and really makes you want to get up in the morning to go to work, and you will find something. I do believe that.
Thank you very much.
So, thank you so much. It was really great. You actually said one thing that I want to sort of end on, and which I really appreciate because it's a great thing to say as an educator myself, which is if the tool doesn't ask you how are you going to think about it, and what I at least took away from that statement was that the tool should ask us questions. The tool should help us to become more curious about the world, and I really, really appreciate that you're thinking that way as a designer, that you're thinking about designing tools that can ask us questions and sort of query us for things. But also, more importantly, you've pioneered and set out on a new direction in your own career, and all of us can take away a lot from that. It's very inspiring, and I think we're all here to do that. We all want to chart our own path, and you've done that very well. So thank you very much. I really want to thank you so much for a great talk. And I want to also say to everyone, we hope that you join us again for the next lecture, where we're going to invite Marion Black. We'll have the opportunity to watch Marion Blackwell give his talk on abstract unions. He will be the 31st Arthur Shine Memorial Lecture. And there's a full list of upcoming lectures on our website, so please look them up on architecture.mit.edu. We hope to see you again either in person or virtually. So thank you again. Really appreciate your time.